Hello, good morning, everybody. Video. Wait a minute, it's starting here. All right, what should we talk about today? I've got a few ideas, but if there are any requests or concerns, I'm happy to hear them. Also, I got ink all over my hand when I was writing up a video for you guys, so it's really nice. Okay, well, seeing as how you guys aren't saying anything, let's homework 2. I haven't seen that. I did see. I should have looked. I did see that you sent an email, but I totally forgot to look at it. Let's take a look real quick here. Let's see. Standard. Homework 2. Some limits. All right. Yes, for sure. Okay. Yeah, we can definitely use some examples that are very similar, but not exactly the same as these. I guess we're not. I was hoping we were getting to the other types of limits, but we're not quite there yet. So I think actually doing problems like we've got here is really excellent. And then we will, if we need to, we will move. If we're able to, we'll move on to start talking about more of the 0 over 0 type of limits, which I know you guys haven't quite covered just yet, but we're almost there. I'm sure he's going to talk about it in class today, I would bet. So let's look at some examples. And I'm really just I'm looking at his homework and I'm going to make up some examples that are very much like what he's got here. So I kind of like to phrase this one this way, but so let's say our sequence was a7 equal to 3n squared plus 5n plus 6 over 2n squared plus n to the 4th plus 2n to the 7th. I want to find the limit as n goes to infinity of a sub n. So, sorry, let me move my video up just a little bit, or my screen up so it can catch things better. Sorry about that. Come on, I've got this makeshift like cup under my thing here. Okay, I can move this a little bit closer too. Sorry, it's always hard to get this exactly positioned in the best way. That's a little bit better, I think. All right, so what's this limit going to be? Well, the degree on top is larger. Sorry, the degree on the bottom is larger. So we know that the bottom is getting bigger faster. So we know that this limit is 0. And for problems like this, I think that's all you really have to say. If the degree on the bottom is larger, right, there's your degree 7 on the bottom, degree 2 on the top. This is going to be 0 because the degree of the top is less than the degree of the bottom. Now let me ask you a different question. What if we instead kind of flipped it and said, what's the limit? The sun is too hot. I want the window open. Let's do this. Okay, sure. The limit then goes to infinity of, I'm going to kind of flip them over, so I'm going to change the top one a little bit. Let's say it's n squared plus n to the fourth minus n to the seventh over 3n squared plus 5n plus 6. So now, same kind of thing, except now the degree on top is larger. The degree on top is larger. And I think we've seen already that when the degree on top is the larger degree, move this over here. Not giving quite so much glare. That's a little better. When the degree on top is larger, you're going to get some sort of infinity because the top part of the fraction is getting bigger faster than the bottom part. Now here's the thing. In this particular one, that's not better actually. The top is getting big, but it's actually going to go to minus infinity because this biggest term here has a negative sign in front of it. So this limit is going to be negative infinity because the degree on top is bigger than the degree on the bottom. And also, the leading coefficients have opposite signs. When the leading coefficients have opposite signs, the top part's going to minus infinity, the bottom part's going to positive infinity. But since the top part's bigger, the whole thing is blowing up. But it is going to a negative overall thing because of this having a negative sign right here and there being a positive sign right there on our leading coefficients. Okay, so let's see here. We can also look at one of the more standard ones. I feel like we've done so many of these. Is 3n to the 7th? Sorry, I'm not sure what your, is that question, is it 3n to the 7th or 3n squared? Yeah, that's a fair question. This is 3n, sorry, my 2's are not always great. That's n squared and that's 3n squared. Sorry about that. You'll know I'm writing a 7 because I always write my 7s with a little line on them like that. My 2 did not have that. Yeah, that's fair. So now it's more clear that the degree on top is 7, the degree on the bottom is 2, and since the degree on top is larger, we're getting some sort of infinity, but it's a negative infinity because of the opposite signs on our leading coefficients. -1 for a leading coefficient there, +3 for a leading coefficient there. Also, feel free to say words. You guys are welcome to talk. I'm happy to hear your questions if you want to say them. This is a little bit loose. Let's see. So let's see what I got here. And then there's, of course, the standard, you know, the limit as n goes to infinity of, I don't know, 1 plus n to the 3rd plus 5n to the 6th divided by, I don't know, 3n squared minus 2n to the 6th plus n to the 4th. In this case, in fact, no, in this case, I want you guys to tell me, either in the chat or with your words, what is the limit of this going to be? Here's a hint. It is a real number. It does exist. All right. So it would be 0 if the degree on top and the degree on it was less than the degree on the bottom. But here, let me ask you guys, what is the degree on top? What's the highest power? Yeah, Gabriella, that is the correct answer to the overall question. So the degree on top is 6. The degree on the bottom is also, well, the highest power of n is 6. Since the degrees are the same, you know, the limit is the quotient or fraction of the leading coefficients. So this ends up equaling, well, the leading coefficients are the coefficients of the highest terms of the highest powers. So it's this coefficient divided by that coefficient, which is going to be 5 with -2 or -5/2. So yeah, so that's our answer there. So sometimes, like in these homework problems, they might try and trip you up by writing the terms out of order. You're welcome to rewrite them if you want to. Like you totally could have first just said, oh, I'm going to rewrite this the normal way as 5n to the 6 plus n cubed plus 1 over negative 2n to the 6 plus 3n, plus n to the 4th plus 3n squared. And then it's a little more obvious, oh yeah, these have the same degree, and the answer is just the quotient of those leading coefficients there. All right, so moving on. Oh yeah, that next question is a good question. So here's the thing with absolute values. A lot of the time, the limit's not going to exist when you have an absolute value divided by something that isn't an absolute value. Well, let's take a look. Oh, actually, so I misread that one. So I'm going to look at a bigger problem, actually. I'm going to look at the limit as x approaches, let's use 6, of the absolute value of x minus 6 over x minus 6. Now, I want to caution you, this is a little bit different than the question he's asked. He did the limit as x approaches 2 just from the left. And we're still going to look at both sides, because here's the thing. When you're asked to find the limit of some expression, for the limit to be able to exist, both the left-hand limit and the right-hand limit have to end up being the same. And I know he said this in class. He actually pointed out as kind of a little theorem. For a limit to exist, the left-hand limit and the right-hand limit both have to exist and equal the same thing. So I'm going to look at the left-hand limit and the right-hand limit. And here's, well, we'll graph this function in a minute to kind of see what it looks like. Here's what we're going to remember. So the absolute value of x minus 6. I know the graph of this function because I know the graph of the absolute value function. Right? Here's the absolute value of x. And then if I wanted to graph the absolute value of x minus 6, I would shift it 6 in what direction? Right? Left, up, down. And the answer is, we would shift it to the right, exactly, because x has to be 6 bigger than it was to get the same results. Right here, if x is 0, y is 0. Here, x has to be 6 larger, x has to be 6 to get y equals 0. So I'm actually going to erase this graph and just graph the parent graph. Sorry, not the parent, the actual graph. So y equals the absolute value of x minus 6 has the vertex at 6, and it looks like this. And here's the thing. This is a piecewise function. This piece of it, this is just the line y equals x minus 6. But this piece here is the negative of that. It's y equal to negative of x minus 6. And that's exactly because if x is bigger than 6, right? So here's x equal to 6. If x is bigger than 6, well, if x is bigger than 6, then the insides are going to be positive, and the absolute value of something positive is just whatever that was. So this is going to equal just x minus 6 if x is already bigger than 6. But if x was something like 3 or 2, 2 minus 6 is negative 4. And to turn a negative into a positive, you have to multiply it by negative 1. So when x is smaller than 6, you have to take the insides of that and multiply by negative 1. And then you can put the equals part on either one because it's the same. I'm going to do it right there. So to see if this limit exists, we actually have to look at the right-hand limit and left-hand limit separately. So first I'm going to look at the limit as x approaches 6 from the right. Okay, so if x approaches 6 from the right, that means x is bigger than 6. And if x is bigger than 6, that means the absolute value of x minus 6 is just the function x minus 6. So this is equal to the limit as x approaches 6 from the right of x minus 6 over x minus 6. But x minus 6 divided by x minus 6 is what? Everybody. I know you guys know it. Nobody wants to say anything. Okay, fine. So x minus 6 divided by x minus 6 is just 1. Now here's the thing. You could probably just say the answer was 1, but I really want to stress that what's actually happening here is that you're canceling these, and then you're taking the limit of 1. But the limit of a constant is always just that constant. So the limit of 1 is just equal to 1. But you might want to see that step, so just be aware of that. Okay, so if you were just asked to find the limit as x approaches 6 from the right, that would be your answer. It would be 1. Now let's find the limit as x approaches 6 from the left of the absolute value of x minus 6 over x minus 6. And now here's the thing. When we approach 6 from the left, that means we are less than 6, like 5 or 4. So if I'm less than 6, I'm over here. So if we're less than 6, then the absolute value of x minus 6 is going to get replaced by negative of x minus 6. And I really want to make it really 100% clear. When you have an absolute value of something, you can't just drop the absolute values and pretend like things work fine. You really have to think about, oh, if I'm bigger than, if we're in a place where the insides are positive, great, it's fine. If I'm in a place where the insides are negative, you have to turn that negative into a positive. Right? If x is less than 6, then the negative of x minus 6 will give you the positive result. Right? Like if x was 2, negative of 2 minus 6 is negative of negative 4, which is positive 4. Divided by x minus 6. And now, these x minus 6's cancel, but we're left with a negative 1 on top. So its limit as x goes to 6 from the left of negative 1. The limit of a constant is still just the constant. So if the question were just, what's the limit as x approaches 6 from the left, the answer would be negative 1. The overall answer to my question is that this limit does not exist exactly because the limit from the left and the limit from the right are not equal, right? So we say that the limit as x approaches 6 of the absolute value of x minus 6 over x minus 6 does not exist because the limit as x approaches 6 from the right of the absolute value of x minus 6 over x minus 6 does not equal the limit as x approaches 6 from the left of the absolute value of x minus 6 over x minus 6. Now, I know that wasn't the exact question that was asked on the homework, but this is definitely something you want to be thinking about when you're looking at these kind of limits. One more thing about this question, just want to show you the graph. So here's the thing. If I was going to graph this, well, first of all, it's totally undefined at 6, right? When you plug in 6, you don't get anything. You get 0 over 0, which is an indeterminate form. Sometimes it's getting close to some number, sometimes it doesn't. So here's 6. Then if you pick any number bigger than 6, so I want everybody in their head, pick any number bigger than 6. Don't everybody pick 7, pick something way bigger than 6. And plug it in. I'm picking 8 because 8's my favorite number. And when I plug in 8, I get 2 on top divided by 2 on the bottom, which is 1. Did you guys get 1 when you plugged in your number? Definitely, right? Of course you got 1, because if you're picking something bigger than 6, the top and the bottom are going to be exactly the same. So if you pick anything bigger than 6, like 7 or 8 or 9 or 8.2 or whatever, you're going to get 1 for each of those. In fact, anything bigger than 6 is going to give you a y value of 1. On the other hand, or other side of 6, it's really saying not the other hand. On the other side of 6, if I pick something like 4, well, what are you going to get when you plug in 4 to the top? You're going to get the absolute value of 4 minus 6, which is the absolute value of negative 2, which is 2. On the bottom, you're going to get 4 minus 6, which is negative 2. So you're going to get 2 divided by negative 2, which is negative 1. And that's going to be true for any number you pick that is less than 6, whether it's 5 or 4 or negative 1,000. So anything over here is going to give you a value of negative 1. And so graphically, we can really see, oh, look, the left-hand side of this function and the right-hand side of this function are not approaching the same y value as they get closer and closer to 6. And that exactly means that's one of the ways we see that the limit does not exist here. Okay. I know, mean girls, yes, okay. It's not like she really evaluated that limit. She was totally just guessing. Seems kind of like garbage. I mean, I'm sure she was good at math, but like, it didn't feel like she was really thinking about that limit very hard. Just thinking about whatever that guy's name was. Can't remember right now. My eyes is totally laughing in the background. Okay, so let's look here. So we did kind of do one like number 4 previously. I'm going to change. Oh, actually, that's a good one though. I think I'll change it up a tiny bit. Sure. Oh, that's a. I don't like. No, that's a weird. No, that's a fine question. Okay, fine. Sorry, I thought he was doing something strange here at first. But he's definitely wanting you to think about this negative infinity thing. So the limit as x goes to negative infinity. I'm going to say, let's make it 3x over the square root of, I have to actually think for a minute here to make sure this comes out right. Sorry, 1 minute. He's doing that times that. Okay, he wants that to happen. Okay, let's do 25x squared minus 4 plus 2. Okay. Which seems like a weird limit. Here's the thing I want you to think about. So before you just start throwing things at a problem, right? Like you told me to start doing something, I would definitely start multiplying by the conjugate if I wasn't paying attention. I'm going to do that anyway. But you really should think about, do you have something that makes sense to manipulate? For example, if I had instead said the question was this, just 3 over that, you wouldn't have to do any work because the denominator is getting really, really large. The numerator is 3, and 3 divided by an ever-increasing denominator would just be 0 because the denominator is huge and the numerator is just small. So make sure you don't just start attacking a problem with methods before you think about, well, what do I really have? Now for this question, we actually have 3x over that. So the top is going to negative infinity, and the denominator is going to positive infinity. And the reason the denominator is going to positive infinity is because negative infinity squared is positive infinity, times 25 is positive infinity, minus 4 positive square root, that's still positive. So we do have what's called an infinity over infinity type. Technically, this is a negative infinity over positive infinity. It doesn't matter when it's division what the signs are of your infinities, whether one's positive and one's negative, or they're both negative or they're both positive. This is always what's referred to as an indeterminate form. And I know he said this in class, it just means it can end up being any value. So infinities over infinities are definitely indeterminate forms. So are 0 over zeros. So are infinity minus infinities. Those are a few of the ones. Well, actually, I don't think we've really seen 1 over 0 over zeros yet, but we're definitely going to see a lot of these. So that's why I keep saying it. All right. So the way you would attack this one is by multiplying by the conjugate. And so you're always going to multiply by the conjugate of the square root thing, right? Like, it doesn't make sense to multiply by the conjugate of this. I feel like my writing is not looking serious. I'll make this. Ooh, I'm going to drop my eraser. Sorry about that. I'm not talking to you. My wife just said, what? I'm sorry. I am talking to you guys. I just want to make that look a little larger. And I'm going to multiply by the conjugate of this. So that's going to be the square root of 25x squared minus 4 minus 2. And then the same thing on top. Because really we can only multiply by 1 or multiply by 1. All right. Whenever you're multiplying by a conjugate, you want to actually multiply with the conjugates and not multiply out the things that are not conjugates. So the top I'm just going to leave as 3x times this whole thing here. So the limit as x goes to minus infinity of 3x times that whole thing there divided by, so when you multiply out the actual conjugates, right, this times this, you always get the first thing squared. That's going to be 25x squared minus 4 minus the second thing squared. So 2 times negative 2 is minus 2 squared, or minus 4. Darn it. I knew I messed that up a little bit. Okay. Sorry, I'm going to change the problem. Do I need to change the problem? Sorry, let me think for 1 second. Sorry, guys. I really do have to actually think about this. Yeah, I need this to be, sorry, one tiny change. I'm going to make this a 25x squared plus 4, which means that's a plus 4. Those are both plus 4s. That's a plus 4, and that's a plus 4. Because I really wanted this to cancel out. Yeah, sorry about that. Sometimes mistakes happen. Okay, so then we're going to simplify. We're going to get the limit as x goes to minus infinity. The denominator is going to be just 25x squared. And for these ones with the square root of something with an x squared, the idea is you're going to factor out the x squared from inside the square root. So I'm going to have 3x times the square root of 20 of x squared times 25 plus 4 over x squared minus 2. Okay, we're getting close. The reason for doing that is that then you can say the square root of x squared is the absolute value of x. And this is where it's important that it's negative infinity. So, no, sorry, get out of the way. So I've got the limit as x goes to minus infinity of, on top I've got 3x times the quantity. So the square root of x squared is going to be the absolute value of x. And then I still have the square root of 25 plus 4 over x squared minus 2, all over 25x squared. Now we're so close, but I think we're going to need another side. So I'm going to go to the other side. I'm going to recopy this. So let's see, I had 3x times the limit as x goes to minus infinity of 3x times the absolute value of x times the square root of 25 plus 4 over x squared minus 2, all divided by 25x squared. Okay, so finally, well, not finally. So in this case, what's the absolute value of x equal to?
Negative x?
Well, let me ask you guys. Is x positive or is x negative?
Negative.
Definitely negative. I don't have my volume turned up very loud. Sorry. If you guys are saying things, I might not have heard you because my volume was turned way down. Yeah, x is definitely negative. And if x is negative, right, if x is less than 0, then the absolute value of x is negative x. So I'm going to rewrite this as, and actually I'm going to distribute this as well. So I have the limit as x goes to negative infinity of 3x times negative x is negative 3x squared times the square root of 25 plus 4 over x squared. Minus 2 times 3x is 6x. At this point, I would probably just say it's negative 3/25 because I have kind of a highest power term and highest power term that's probably a little bit hand wavy. What we should really do at this point is divide everything by the highest power of x in the denominator, which is x squared. So I'm actually going to do one more step. I'm going to write this as the limit. As I don't know why I wrote that line like that. Let's try that again. Limit as x goes to minus infinity. I'm going to divide each term by x squared. So I'm going to have, that's going to look gross, negative 3x squared times the square root of 25 plus 4 over x squared. Let's do it like this. Divided by x squared. And then I'm going to have minus 6x divided by x squared all over 25x squared divided by x squared. And here's what happens. The x squared here, let me use this pen. Use a pen that's dying. Where's my dying pens? Oh, over here. Dying pens are good for writing in other pens because they get kind of grossly colored. So this x squared here cancels with that x squared there. And x here will cancel one of the x's here, so I'll have 6 over x. And this x squared here will cancel with that x squared there. Okay, so here's what I'm left with. I'm left with the limit as x goes to minus infinity of this mess, the square root of 25 plus, oh, I forgot something, I think. I forgot the negative 3 out in front, sorry. Negative 3 times the square root of 25 plus 4 over x squared. Minus 6 over x all over 25. And finally, we can say, okay, 6 over x goes to 0. 4 over x squared goes to 0. And I'm left with, I see I would have been wrong if I said the answer was negative 3/25. I'm left with negative 3 times the square root of 25 all over 25. Which is negative 3 times 5 over 25, which is negative 3/5. It's kind of a long problem. And my hand looks so gross with all this pen on it. Okay. So I do think the problem he has assigned you is pretty much about all those steps. Like you kind of have to do all of that. Yeah.
I had a question
Yeah.
about the absolute value. So
Sure.
for this problem, the absolute value of x is equal to negative x, but like, is that only in the case of when the limit is x to negative infinity, or is that like a universal rule?
I would say it's the case whenever the limit is x approaching some negative value. So if we're only talking about infinities, yeah, it'll be when x is approaching negative infinity. If this question where the limit is x approaching positive infinity, then we would have had absolute value of x turning into positive x. But yeah, that's kind of the key thing about this problem. It's a good question. All right, let's talk about limits. More about limits. So I'm going to draw a picture. Here's a piecewise function. F of x is equal to, let's make it easy, x squared when x is less than or equal to 1, and 3x when x is greater than 1. Sure, it's a little bit similar to what he did, but nothing. Does the limit exist as x approaches 1? So what is the limit as x approaches 1 of f of x? There's a couple ways to think about this, but I think graphically is, and I don't always want to draw the graph, but I want you guys to be able to think about, oh, the graph looks like this, it means the limit probably doesn't exist. So I'm going to graph this. So when I'm graphing this, it's x squared up until x equal to 1. So I know y equals x squared looks like this. There's my usual y equals x squared, but I'm going to stop. Wow, that's a 2. Sure. But I'm going to stop when I get to x equal to 1. So if x is less than or equal to 1, so everything to the left here, I'm going to get the x squared function up there. So I'm drawing it here. I'm getting all that. And then y equal to 3x, that's just a straight line that goes to the origin. It looks like that. And if I was starting at 1, well, if I plug in 1, 3 times 1 is 3. So I've got the point 1, 3. So the part I want is just the part starting here is not including that point because it's when x is greater than 1. I want everything to the right of that. So I'm starting at the point 1, 3, but it's an open circle because I don't actually want to include that point. And then I'm just going up like that. So let me ask you, the way I've graphed this, does it look like the limit from the left and the limit from the right are the same? Yes or no? Yeah. Don't forget, you guys can also use the little yes, no buttons if you want. I like those little buttons. Those are, whoop, I just did something. Where'd the chat go? Okay, anyway. If you want, you don't have to, but you can. I like them. Yeah, definitely not. Right, the limit from the left, and so I kind of like to do this, right? As we're approaching 1 from the left, the function is approaching also 1. So I can say here, okay, look, the limit as x approaches 1 from the left of my function is equal to +1. As I approach 1 from the right, the function values are not approaching 1. They're approaching a value of 3. So the limit as x approaches 1 from the right of f of x is clearly equal to 3, +3. And since the limit from the left and the limit from the right are not the same, that means the overall limit does not exist. So we'd say, oh yeah, the limit as x approaches 1 of f of x does not exist. Now I do want to point out, you don't have to graph this function to see that the limit doesn't exist, but it's good to be able to think of the graph. The way we usually end up showing that functions that are piecewise like this either are or are not, or have a limit that exists or not at a particular point, is just to do them. So if I'm going to find the limit as x approaches 1 from the left of f of x, what I'm going to do is I'm actually going to use the piece of the piecewise function when x is to the left of 1. So let me ask you guys, if x is to the left of 1, am I using the top piece or the bottom piece?
Wait.
Oh, sorry, I can't see the messages because I clicked something dumbly. Yeah, top. Excellent. That's where x is less than 1. Sorry, I need to, if I'm asking questions, I need to be able to see the answers. So I'm just replacing the function with the piece of the function that is in the domain that makes sense. And then I can just use the evaluation idea and plug in 1 for x and get 1 squared, which is 1. You shouldn't be plugging in something that is less than 1. Like I just talk about like how you're getting like 0.9 or 0.999, whatever, but you actually want to plug in 1 because again, we're not trying to see what value we are almost. We actually want to see that we are getting closer and closer to 1. Even though you might not actually, well, you actually do get to 1 here, so that's not a good example. Let's look at the other side. So if I approach the limit, if I take the limit as x approaches 1 from the right of f of x, well now I'm going to end up using the bottom piece of the function because that is when x is to the right of 1. Now I've definitely seen people do something like plug in 2 here and get 6 because they're like, oh, it should be a little bit bigger than 1. No. Even though we don't actually get to 1 from the right, we're still going to plug in 1 and get 3 times 1, which is 3. And again, what that says, when I say that the limit as x approaches 1 from the right is equal to 3, the meaning I'm conveying there is that as x gets closer and closer to 1, but not actually equal to 1 from the right, the function values get closer and closer to 3, but not necessarily actually equal to 3. So just be aware, right? We don't actually care what's happening at 1. We just care what's happening on either side of 1. Okay. Yeah, it's a good question. Seeing that about 10 minutes, sure. So let's see. All right, so I'm gonna, yeah, all right. So I'm gonna skip around a little bit for these last couple ones because we only have like 10 minutes left. So when someone asks you to find the horizontal asymptote, they're really just asking you to find the limits to infinity and negative infinity. So if I said find the horizontal asymptote for y equal to 2x cubed plus x plus 1 over 5x cubed plus 2x squared minus 3, you could take the limit to infinity. You say, okay, limit. Now I'm not actually going to really do the work. You guys already know the answer before I even try to write it down. The answer is what?
2/5.
Exactly. The limit to infinity, if it exists, is the horizontal asymptote. So the horizontal asymptote is the line y equal to 2/5. Now, something to know. For a nice rational function like this, where it's just a polynomial on top and a polynomial on the bottom, meaning positive integer powers of x, the limit to infinity and the limit to negative infinity will always be the same, meaning you only have one horizontal asymptote. Whatever it is to the right is also the same as it would be to the left. If we have negative infinity, 2x cubed plus x plus 1, 5x cubed plus 2x squared minus 3. That would also equal 2/5. Now I'm not going to do this other one because we already did one time. So if you look at question 8 on the homework, it's exactly using the limit that we did in question 4. So I'm going to remind you, gosh, the question we did, which I'm going to have trouble recalling here, I believe it was the limit as x approached negative infinity of, oh God, I think it was, let me try to guess at this. I believe I made it 3x over the square root of 25x squared plus 4 minus 2. Pretty sure that's what it was, right? And we got the limit equal to 3/5. So here's the thing. I could say that 3/5 is one of the horizontal asymptotes for this function. But here's the thing. You also have to take the limit as x goes to positive infinity of this. And that's actually going to give you a different value. So for ones like this, where you have like this weird square root of x squared thing, you often get two different horizontal asymptotes. One to the left, in this case it's positive 3/5, and one to the right. Gosh, I don't really want to do the work for it, but I guess I could. Where'd my eraser go? I'm losing my mind and my eraser. Like really, I haven't moved from this spot. Oh, it's on the floor. There it is. Hiding on my carpet. So I'm not going to do all the work for this one because we already did it. So if you look back, right, when we were doing the limit as x goes to negative infinity, we did all this stuff. We got something like, geez, okay. We had 3x times the square root of 25x squared plus 4 plus 2 because we multiplied by the conjugate. And the bottom ended up being just 25x squared because it was plus 4 minus 4 and those canceled. And then we did the thing where we brought up the x squared. So in this case, when I bring out the x squared here as the opposite value of x, because it's the square root of x squared, what happens here is that now, since we're going to infinity, this x just becomes, this opposite value of x just becomes x. So I end up with the limit as x goes to infinity of positive 3x squared. I feel like I made I think I might have said something wrong over there. I'll come back to that in a minute. Times the square root of 25 plus 4 over x squared plus 6x all over 25 over x squared. I think our answer before was -3/5. If I didn't say that before, I'm pretty sure it should have been, right? I think we had a -3 that I might have lost along the way. So that limit was -3/5. What you're going to end up getting here is that this one's going to end up being +3/5 because we're going to divide everything by x squared. And then we're going to take the limit, and this is going to go to 0, and this is going to go to 0, and you're going to get +3 times the square root of 25 all over 25, which is 3 times 5 over 25, which is 3/5. So what often ends up happening with these kinds of questions is you get y equal to +3/5 as your horizontal asymptote on the right, and y equal to -3/5 as your horizontal asymptote on the left, which is kind of funny. But that's definitely what he's going for with question 8. I really want to do all of them. So let's get to question 10 first. Question 10. You know what? I'll make a video about question 10 because there's a lot more to say about question 10, the squeeze theorem. Oh no, there's not. I'm a liar. Never mind. Squeeze theorem. Okay, great. Question 10. Something similar. So first, it's important to know this. The limit as x goes to infinity of sine of x over x is equal to 0. Now, we actually have to do some work to show this, but it is true. Here's the work we're going to do. So here's kind of the clues. The clues that I need to use the squeeze theorem. So here are some squeeze theorem clues. You have a limit to infinity, and you have either sine of x or cosine of x. If you see those two things together, it is usually a very good guess that you're going to have to use the squeeze theorem. And the beginning is always going to be that you're going to start by saying, well, sine of x or cosine of x is always between 1 and -1. That's always something that's true, right? Think about the graph of sine and the graph of cosine. They keep going up and down like this, but the highest it ever gets to is 1, and the lowest it ever gets to is -1. And then I'm going to take this compound inequality, and I'm going to try and make the middle part, always the middle part, look like the thing I'm trying to take the limit of. So I'm going to divide everything by x. So I'm going to have -1 over x is less than or equal to sine of x over x, less than or equal to 1 over x. And then we're going to take the limits of the outer parts, the outer limits, if you will. So the limit as x goes to infinity of 1 over x, well, that's 0. The limit as x goes to -infinity of 1 over x. As x still to positive infinity, right? We're always going to infinity of -1 over x, excuse me, is also 0. And then we can conclude if these outer limits are the same value, then the middle thing gets squeezed to that same value as well. By the squeeze theorem. So that's the whole idea of the squeeze theorem, is you try to get this thing to be between two things whose limit that you can find and end up being equal to each other. Let me do, I know we have like 1 minute, but let me do another example like this that's more similar to what he's got going on in question 10. And I'll try and make a video of difference equation stuff today to post for you guys. because I know a couple of you had questions about that from your from the reflections. Some of you said you'd like to see some difference equation stuff. So I will try and do an example that's similar to that homework question, but not exactly the same. So, oh, the geez, the link to the sign-in. Yeah, good call. Again, I encourage you all to bookmark it or something so you can just go there when we have class again. Only sign in once. I think a couple of you actually signed in twice last time, which is fine. But if the numbers don't match for me, I'm like, oh, what's going on? So try to only sign in exactly once. But I want to do one similar to this, which isn't too bad. So let's say I want to do the limit as x goes to infinity of 2x squared plus 3 cosine of x over 5x. Why 2/5 every time? I don't know. It's just because of what my brain is doing today. So here's the thing. If you ignore this cosine for a second, you have a pretty good guess that this is going to be 2/5 because this looks a lot like our usual rational function kind of thing. And you would be right. It is going to be 2/5. The issue here is that if you just say it's 2/5, a lot of teachers are not going to be cool with that. They're going to be like, oh, you didn't show your squeeze theorem work. So here's the work you can do. And there's actually 2 good ways to do this. So I'm going to try and show you both real fast. You can always watch the video upload later if I'm going a little too fast right now. So one way to do it is to, and this is probably the way I think your teacher would prefer you do it. Maybe not, I don't know. It's hard to say. Is I'm going to start with this. Sorry, I'm going to start with cosine. And then I'm going to manipulate this cosine so it ends up looking like all of this. So first I'm going to multiply everything by 3. Then I'm going to add 2x squared to everything. Then I'm going to divide everything by 5x plus 1. Instead of writing a whole new line, let's just divide everything by 5x squared plus 1. So basically, another way you can think about doing this is you can just say, oh, I can just take this whole expression, replace cosine with positive 1 to get the right-hand side, replace cosine with negative 1 to get the left-hand side, and that will totally give you the inequality that you need. And then check this out. We know the limit of this and this because these are rational functions like we know how to take the limit of. This limit as x goes to infinity of 2x squared plus 3 over 5x squared plus 1 is 2/5 because the degrees are both 2 and the quotient of the leading coefficients is 2/5. Likewise, the limit as x goes to minus infinity of 2x squared. Sorry, I keep making that mistake. I'm sorry. It's always the limit. Sorry, x should always be going to whatever x is going to here. You shouldn't be changing it to plus or minus infinity. I'm sorry I made that mistake twice. It's wrong. X is going to infinity, but now we're doing the limit of this piece. But we can see that's also going to be 2/5 because of the same thing, right? It's still a rational function. Degrees are the same. Leading coefficients are 2 over 5. And so then we can say, well, since the right-hand thing has a limit of 2/5 and the left-hand thing has a limit of 2/5, this middle thing has to get squeezed between. So we can say, by the squeeze theorem, the limit as x approaches infinity of this middle thing, 2x squared plus 3 cosine x over 5x squared plus 1 has to equal 2/5. So that's, I think that's probably the better way to do it. So I would encourage you to do the one on your homework like that. So you'll start with sine of x between 1 and negative 1, and then you'll add 3 to everything. Sorry, you'll add negative 3x to everything, and you'll divide everything by x plus 1. And so the limit for that should end up being negative 3. All right, I've gone over time. We should stop there. I will post this up on Canvas, whatever, YouTube, the usual stuff. Make sure you do the attendance. And I've also got a couple other videos I'm going to try and post today as well. So I'll see you guys on Friday. I should actually end the meeting.